Hi, good morning, everyone. Today I'll be presenting the paper titled An End-to-End System for Culturally Attuned Driving Feedback. This work focuses on building an intelligent safety system specifically for the Nigerian context. It is actually done by myself, um, Dr. Dewey Yi, as well as Professor Ehud Reiter. Of course, we are all from the University of Aberdeen, and the work was supported by the Tertiary Education Trust Fund. So let's start with the context. Um, Road safety is a massive public health crisis in Nigeria, which is our focus area, with over 5,000 fatalities annually. So the core issue isn't just bad driving; it is that we can't just copy and paste Western tech solutions in the Nigerian context. Why? Because the Nigerian context or Nigeria faces unique challenges such as poor physical route infrastructure, unreliable internet, or unreliable internet connectivity, as well as lack of digital road data. In fact, the unreliable internet connectivity actually breaks cloud dependent apps. It breaks them because um, when connectivity is lost, of course, the apps can't actually run as expected anymore. So our system then, our solution, our system functions as a four-stage pipeline that is designed to transform raw data into intelligent feedback. So we begin that process with data collection, where we capture real-time telemetry data through the mobile phone sensors such as GPS, accelerometer, um, linear accelerometer, this other one, gyroscope, and the rest. So when this data is collected, our offline data processing stage or phase, part of the system then processes this data and then stores results in a local room database for efficiency. Now, the core intelligence of this system resides in the behavior analysis engine. Here, we actually combined we actually combined an FFT analysis for motion classification, rule-based logic to catch events like speeding or swerving, and a specialized model to detect alcohol influence. Finally, these insights feed into our feedback generation system, where we leverage large language models such as ChatGPT and Gemini, as well as a RAG technology to generate instant safety tips and detailed post-drive reports. Now, the heart of our contribution is actually this dual component natural language generation engine. Now, why did we build two components? We built these two components because we have two different goals. One, for immediate safety tips. And now for this, we need absolute legal accuracy because we can't actually have the AI to hallucinate traffic laws. Then the other for weekly reports. Here, we need psychological persuasion to actually change people's or drivers' behavior. So we split the engine. One, one pipeline handling the facts or the legal facts, and then the other handling the psychological persuasion. Moving on to our results. So in component one, or the component one actually demonstrates our system for generating the legally grounded tips using a naive RAG approach. The process is triggered immediately when unsafe events are detected. These events, of course, like we mentioned earlier, include hash braking, hash acceleration, swerving, and the likes. Now, this initiates a naive retrieval phase where the system performs a keyword-based search against our local JSON database containing the Nigerian Highway Code as well as the Nigerian Traffic Regulations Law. Finally, these regulations are then injected into the LLM prompt, enabling the model to generate a safety tip that is not only concise but also strictly aligns with the local traffic laws. The second component generates reports. Here we ground our prompts in the theory of planned behavior, focusing on attitudes and norms. We implemented a novel two-step reflection pipeline that ensures quality. So first, a, a model, an LLM model, which is ChatGPT 4, generates a comprehensive draft. Then a reflector step criticizes or critiques that draft, checking for tone and safety compliance before the next version of ChatGPT, which is GPT-4o mini, polishes the final output. This mimics a human editing process to ensure the feedback is supportive and not accusatory. We also addressed a specific local crisis, which is drink driving. Standard phone sensors actually can't smell alcohol, so we built a specialized machine learning component. We used the decision tree model because it was, it is because of its interpretability. It analyzes proxy features like time of the day, whether it was late night or not, day of week, and then variance in speed and steering. Now, in our testing on a local dataset, this model achieved 100% recall. Now, why did we make recall a case in point? We made recall a case in point here because a miss of an alcohol influenced driving is a critical issue in road safety, and that was why we were more keen on the recall. So to optimize this model, we use the ONNX runtime to run on the phone in under 50 milliseconds, allowing for real-time um, transmission of that result either to the database or to an LLM prompt that needs it. We didn't just build this in a lab actually. We deployed it in real life in Nigeria. In it, of course, the pilot study. In the pilot study, we recruited about 90 drivers across 4 major cities in Nigeria, including Abuja, Lagos, Port Harcourt, and then Yenagoa. Over the study period, we collected over 2 million data points and detected about 154,000 unsafe events. This large-scale deployment served as a critical stress test, proving that our offline first architecture and data pipelines are robust enough for the real world. What you see on the screen right now is a snapshot of the behaviors that we analyzed in the pilot phase of the deployment experiment. The most common unsafe behaviors that we observed or that we got were harsh acceleration and harsh braking. This aligns with local observations of aggressive driving due to traffic congestion. This data confirms that our rule-based engine is effectively capturing the specific types of risk driving or risk driving habits that are prevalent in Nigeria. In conclusion, we've demonstrated that it is possible to build advanced AI safety systems for low resource settings. We successfully combined strict legal constraints with persuasive AI in our dual NLG engine. Our findings highlighted the prevalence of harsh acceleration and the technical challenges of sensor variability across different Android phones. Moving forward, therefore, our immediate next step is a comprehensive mixed method study to statistically measure if this feedback actually changes driver behavior over time. Excuse me. Thank you very much for your attention, and I'm now happy to take any questions regarding the system architecture, the NLG app pipelines, or our pilot deployment results. Thank you.